Hello, my students. This is a brief overview of the standard enthalpy of formation. First, standard state. That is the general thermodynamic given conditions. We dealt with STP for gases. Well, for other basic reactions, the standard state is 1 atm and 25 degrees Celsius. Room temperature and normal room pressure at sea level. If we are dealing with a thermodynamic quantity at standard state, you'll see the thermodynamic term with this little elevated kind of degree sign. So delta H naught, if we want to call it, that references that we're at these conditions. Oftentimes, an element has more than one form of itself. For example, carbon. Carbon can be found as diamond, but also as graphite. And we're actually also finding, just with more understanding of nanotechnology, some other forms of carbon, not quite calling those allotropes yet. Phosphorus exists in the red and the white form. Oxygen can exist as ozone, or the oxygen that we of course require for biological function. The reference form is the most stable form of our elements or the compound at the standard states. So it's interesting that actually carbon is most stable thermodynamically as graphite. And we'll learn how we make that conclusion to come. All right. So what is the standard enthalpy of formation? The standard enthalpy of formation is given the connotation of delta H sub F. Now, also called the standard heat of formation. All right. This is the amount of energy released or required to make 1 mole of your compound from the elements in their standard state. For example, if we were going to make 1 mole of sodium chloride, we would, to get the enthalpy of formation, look at the energy required or released to make 1 mole of product from its elements in their reference form at standard state. So we know that chlorine is diatomic and a gas at these conditions. Well, to deliver 1 mole of our product, we need 1/2 a mole of Cl2. Sodium is a solid, and for 1 mole of sodium chloride, we need 1 mole. So by reacting these quantities from sodium solid and chlorine diatomic gas, the energy that's released or absorbed is the standard enthalpy of formation. If we would make sucrose, the standard enthalpy of formation would be experimentally what we would get from carbon graphite, and we know that we'd be reacting, need more room. And I would need 12 moles of that, plus, and we know that hydrogen, diatomic, reference form at standard state, I need 11, plus, what do I do here? Well, strangely, but this is when we can, manipulate and have fractional coefficients. Bleh, not really comfortable with that, but 11/2 O2 will give us the 11 oxygen that we need. Okay. Now, what we found thermodynamically is that actually another way that we can get the enthalpy of the reaction is if we look at the enthalpy of formation that our products have versus our reactants. So we can actually get the enthalpy of a reaction by looking at the summation of the enthalpy of formation of our products minus the summation of the enthalpy of formation of reactants. If I can read specifically for you from your textbook, the enthalpy change for the reaction can be calculated by subtracting the enthalpies of formation of reactants from the enthalpy of formation of products. And the derivation of this is found within your book. Now, where do we find these enthalpies of formation? And I will provide this, at the back of your book, there is a listing. Now, in this chapter, we're only concerned with enthalpy, but in 16, we'll deal with enthalpy, Gibbs free energy, and entropy. There's three main thermodynamic terms. As you can see, these enthalpy of formations, which we already went through how we derive those, is listed, and they are listed alphabetically. And if we want to just look at a reference, why is carbon the reference form graphite? It's thermodynamically favored. Diamond is a very, very, very close second. And if you look at the units, they are in kilojoules per mole. You would be provided this, you would just have to be able to find the values and interpret them correctly per your reaction. So if we just dig in to this first example, use the enthalpy of formation to calculate the heat of vaporization. So transitioning from the liquid to the vapor state is vaporization. So we're looking at the enthalpy of the reaction, but it specifically is the enthalpy of vaporization. We're transitioning between carbon disulfide liquid to carbon disulfide vapor. The enthalpy of my reaction is the summation of the enthalpy of formation of my product minus the summation of the enthalpy of formation, standard state, of my reactant. Now, usually we have multiple reactants and so on, but this gets us started. Now, remember that these values are given in kilojoules per mole. So it's per my balanced reaction. Now, lucky here, I'm only dealing with 1 mole of carbon disulfide gas. And we want to look under the category in which we find our elements or our compounds. So for carbon disulfide, I first would find carbon and see if I can find, nope, so it must be under sulfur. Looking back. This must have been one that was just provided in the textbook and not given. The enthalpy of formation, and if they're not in the table, I will definitely provide them, of the carbon disulfide gas is 117 kilojoules per mole, positive. And we're going to subtract from that, and we have 1 mole of our reactant also. And the enthalpy of formation of the liquid state is 87.9 kilojoules per mole. And so, being just very careful with our math, we get 29 kilojoules per mole. So, taking a look at this reaction, we would have to take care that we get the right values as well as apply the correct coefficients for our reaction. So I'll just go in order. I'm first going to need the enthalpy of formation of nitrogen monoxide, gaseous state. So I'm going to look under nitrogen. Oh, right there. 90. And these would limit our sig figs. Enthalpy of formation of water in the gaseous state. It's negative 242 kilojoules per mole. Enthalpy of formation of ammonia gas is negative 46 kilojoules per mole, and oxygen gas, 0. Now this brings up a wonderful point. The enthalpy of formation of an element in its reference form, its standard state, is 0. So remember, we saw that for carbon graphite. If you would look through your appendix, you'll see that for the elements in their standard state, reference form, its standard state, the enthalpy of formation is 0. Okay, so being very careful to just input things where we need them. The enthalpy of the reaction will be the summation of the enthalpy of formation of the products minus summation of enthalpy of formation of reactants. So again, just being very careful. So I have 4 moles of NO, and I will multiply that by my 90 kilojoules per mole, plus 6 moles of water vapor, negative 242 kilojoules per mole. I will subtract from that 4 moles of NH3 times negative 46 kilojoules per mole, plus 5 moles of O2, but of course multiplied by 0. Again, being just very careful about our math, being careful when we add and subtract with our decimal places, we will get negative 910 kilojoules as our answer. There's another example on the following page, but I believe these two give us good guidance as to how to apply standard enthalpies of formation to get the enthalpy of our reaction.